Okay, let's get started formally for today's session. Week number 6 of this semester, spring 2021. And today, hopefully, in the first session, we'll be able to wrap this topic up, which is, you can say, some concepts which are related to CNNs, right? We have spent last couple of weeks on this. So today, we'll be concluding this general discussion. And then in the second session of today, we'll be discussing some popular CNN architectures that are publicly available, and you can try them to solve your own problems, right? But that would be coming in the second session of the day. So just a quick reminder of the global picture that what we were looking at. So the last topic that we started was regularization techniques. Okay, so regularization techniques, as we discussed in the beginning, their objective is to reduce overfitting, right? That you make slight modifications to your learning algorithm, and the objective is that we want to reduce overfitting. Okay, and few of the regularization techniques, rather to be precise, 3 regularization techniques we have already seen: dropout, data augmentation, and early stopping. In dropout, we randomly, you can say, drop few neurons at the training time, right? So that your network is not too much dependent on a specific set of neurons. Then if you have limited data, so if the data set is small, this could also be a cause of overfitting. So we said you can mitigate that using data augmentation, where we create different copies of the same data. Okay, so maybe for a human eye, those examples are not very different, but for a computer, since it's a different matrix, so it's totally a new example. So this is a very common technique. And then finally, we had seen early stopping, where in addition to training set, we keep a part of data as a validation test, and we keep on checking that if there's a point where the training loss is decreasing, but the validation loss is increasing, so it's a signal that the model might be suffering from overfitting. Right? So we stop prematurely before the total number of epochs have exhausted. So today we will see this last one. In fact, it should be the first one because this is the most common one. But since last time we already had quite a heavy session, so I swapped the order of these techniques. So today we'll be looking at L1 and L2 regularization, right? Which is actually a very common, you can say, regularization technique. And then we'll, in the towards the end of the first session, we'll be looking at Bash normalization in detail, right? I'll come back to that later. First, let's conclude this discussion on regularization techniques by looking at what L1 and L2 regularization are, right? So as we discussed in our previous lecture, that whatever loss function you have, say categorical cross entropy or binary cross entropy, right? So in L1, L2 regularization, you add an additional term to your loss function, right? And this is called a regularization term. And why do we add it? Because we want to penalize the weight matrices when the neural network is learning. And the idea is to push some of the weights close to zero. So that actually translates to a relatively simpler network, and which eventually, or which in turn helps us reduce overfitting. So to add more details to this and be more specific, there's a slight difference between L1 and L2 regularization. I'll explain these in detail. So you see, whatever loss function you are using, so this is the original loss function depending on whatever your problem is. And the term you see on the right side, which I have highlighted, this is the regularization term, right? So what is this? Lambda is a regularization parameter. This divided by 2 we have done for simplification, right? Nothing else. The important term is this one, right? That we are taking the square of all the weights and adding them together, right? For example, if my network has 3 weights, so it actually means W1 square plus W2 square plus W3 square and so on. You are adding them, okay? So we'll see in more detail this expression. This is just an introduction that what actually the expression is. If you talk of L1 regularization, it's very much similar, but the only difference is that instead of squaring the weights and adding them, you add the absolute values of all the weights. Right? So if you have 3 weights, for example, W1, W2, W3, so with L1 regularization, this is the term multiplied by lambda, which is a regularization parameter that you will add to your loss function. Okay, so now we see in detail what actually is the difference between these two and how it helps to shrink the weights, right? How it pushes the weights towards zero, because that was our primary objective. Okay, so maybe I'll do some, you can say, detailed derivation on the board so that you can follow it stepwise. Okay, so let me just write where we started. So we say your cost function is whatever loss function you have originally, and plus, let's start with L2 regularization. So this is the term lambda by 2, and then you take the sum of, you can say, square of all the weights. Okay. Now, if we write it formally, so let's denote the cost by a symbol J, right? So loss is actually, you compute the loss over all the training example, right? So whatever loss function you are using, some loss function L, where you have the true value and the predicted value, right? So yi is the true value for training example I, yi hat is the predicted value, and using, depending on your problem, you will have any loss function. So what you do is you sum the loss on the complete training set. Say you have m training example, and you can normalize it by 1 over m, right? So this is the expression we have seen many times before, right? So similarly, here you have lambda by 2m. M is the total number of training example. Okay, so we are just normalizing it by total number of training example. Okay, so it becomes something like this. Okay, so since the first term is the standard term which we have been using, so we're not much interested in this one, right? So I'm just denoting it by a symbol, say J naught, and this is J, which is the total cost, right? So I'll be more interested in this second term, which is the new term that we have added, and then you have summation, something like this. Now, when we compute the cost, so actually in the weight update, we have to take the derivative of this cost, right, with respect to weights. So this actually is the derivative of J naught, which is the original term from gradient descent. And you also take the derivative of the second term, which is the new term that we have introduced due to regularization. Okay. So again, this first term is standard, so we are not much interested in this one. Let's compute the derivative of the second term with respect to W, right? So in order to compute this derivative, it's a good idea that if 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 we see what actually this term is, you are adding square of all the weights. So as I told you, if I have 3 weights, so this actually means it is something like this. Okay, and if you have n weights or k weights, the expression is something like this, right? You are taking the square of all the weights, adding them together. Now, if I take the derivative of this term, this expression with respect to, say, W1, so what will happen? All the terms except W1 would be constant, their derivative would be 0, and I will only be taking the derivative of the first term, right? Similarly, if I take derivative with respect to W2, so all the terms are constant, so their derivative is 0, and I will effectively be taking derivative only with respect to the term which involves W2, right? So if we take any example, right, for example, say Wi, so all the terms except Wi would map to 0, and the derivative of Wi square would actually be 2 times Wi, right? Just like derivative of x square is 2x. So it's the same thing. So it means if I take its derivative with respect to W, I'm left with only one term, right? If I take derivative with respect to W1, I am left with W1. If I take derivative with respect to W2, I will only be left with W2, right? And so on. And of course, we'll have a 2 coming from the derivation as well. And that was the reason we added a 2 here so that it cancels out. So eventually the derivative would be 2w of this term, and then this 2 and this 2 can cancel out. So I will write it in a simplified way. So it would be J naught W plus lambda by m W, right? So this is basically our key expression If you are not familiar with derivatives, you can ignore the discussion of the last couple of minutes. But if you are familiar with derivative, it's good you know how we arrive at this term, right? So now let me just clean it a bit and rewrite this expression at the top because we have to do something else. So eventually the expression we found was derivative of cos function is derivative of J naught, which was the original term in gradient descent without any regularization term. And we have this additional term lambda by m times w. Okay, so this is basically what we ended up with. Now, why are we computing all this? We are computing this because we want to update the weights. And the expression to update the weight is the original value of weight minus learning rate times derivative of cos function with respect to w, right? This is your you can say key expression which we almost use in every lecture to update the weights. Okay, now we can plug in the value of this derivative in this expression. So what do we get? We get w minus learning rate, and here I will plug in j naught w plus lambda by m w, and I can rearrange it like w minus learning rate into lambda by m w minus learning rate derivative of j naught and w. Okay, now you see again. Let me rather do one more simplification and then we discuss. I can take w common from the first two terms, so it becomes basically 1 minus learning rate lambda by m into w, where w I have taken common, minus learning rate derivative of j naught with respect to w. Now, this last expression is actually your key expression. If you compare it with the original gradient descent, right? So you have a new term which was not present in the original gradient descent, which is actually this part. This is the new term. If I remove it, then this one and this one was actually the original expression of gradient descent. Now, what actually is happening is that, let me write this expression on the top and then maybe we discuss further. So the final expression that we got was, this is something like 1 minus learning rate lambda by m times w, and then we had derivative of j naught with respect to w. Okay, so now you see basically previously if I write the original equation, so it was something like w minus, so that we can compare. Okay, so this is original and this is with L2 regularization. Now let's see what is happening here. Suppose this term, I'm just taking a hypothetical example just to explain it, right? Suppose this term, it comes out to be say 0.2, okay? And so what actually will be happening? 1 minus zero point 0.2 is 0.8. So this would actually become something like 0.8 W minus, okay, this is just an example. So now you see here you are subtracting from W, and here you are taking 80% value of W and then subtracting, right? This term is same, the second term. So you are subtracting the same thing. Suppose you are subtracting 0.1 and the original value of W was say 0.5. So in the first term, you are updating the weight, it becomes 0.5 minus 0.1, which is 0.4. And in the second term, you can say weight update with L2 regularization, you are taking 0.8 W, means 80% of whatever the value of W is, right? So 80% of 0.5 is say 0.4. So zero point 0.4 minus 0.1, which where you get 0.3. So now you see this is actually called weight decay. Now, whatever is the value of W, as a result of L2 regularization, you are taking a proportion of that value, right? 0.8, 0.9, it depends upon lambda m and learning rate, right? But you are not subtracting from W. You are taking, say, 80% or 90% of W and then subtracting. So it means if you are subtracting from a small value, then you are likely to end up close to zero much quickly as compared to if you're subtracting from one, right? So this was our primary objective, that we wanted to push weights close to zero. And this is basically somehow we are achieving that, right? That instead of subtracting from W, we are subtracting from some fraction of W, right? So I'll again give you a recap of all these steps on the slides, but let me just quickly first do it for L1, and then together we see both of these, right? I once I give you a recap of both of these techniques, so it's a good idea that we do it together for both, right? So you see, in case of L1 regularization, you just have a slight change, that the cost function is whatever loss you have plus lambda lambda, and you have, instead of square, you just add the absolute values of the weights, right? And if we write it formally, so we call it J, we call it, say, J naught, right? And for all training example, we normalize it by the number of training example, right? And it becomes something like this. So again, we have to take the derivative of this expression with respect to W. So derivative of J with respect to W is derivative of J naught with respect to W, and plus you have to take derivative of the second term, which is again the new term that we have introduced. So you see, again, if I ask you what is the derivative of mod of X, right? So if you see some book of calculus, rather, let me tell you intuitively, mod of X is like this, okay? Because you only have positive value. So in this part, the derivative is +1. And in this part, the derivative is -1, okay? So basically, it does not have a single value of derivative. It has, if X is positive, the derivative is +1. If X is negative, the derivative is -1, right? You can actually see that this is 45 degrees, this 45 degrees. So derivative of mod of X is actually +1 or -1, depending upon what is the value of X, right? So another way of saying it is that we write it normally as derivative of mod of X is actually sine of X. So if X is positive, the derivative is plus. If X is negative, the derivative is -1, right? So this is a standard new way of finding the derivative of an absolute value. Now here, instead of X, we have variable W. So when we take its derivative, so we'll say derivative of this term is sine of W. If W is positive, you get +1. If W is negative, you get a -1, right? So let me just write that derivative. So this term would be the original term plus lambda by m, and here I can write sine of W. Okay, so this is, you can say, our final expression. Now we can plug in this expression into the weight update equation, and we see where do we end up, right? So the weight update equation in this case will become W, the previous value of weight, minus learning rate into J naught and lambda by m sine of W. Okay, we can slightly rearrange this expression and can say, okay, this is W minus learning rate lambda by m sine of W minus learning rate of this thing. Okay, again, now you see what actually is happening here. This is the original term of gradient descent. Okay, this is the original term, and this is the new term. So now what is happening? From W, you are first subtracting this thing and then subtracting the derivative of error. So if, for example, W was, say, 0.5, okay, and suppose this whole comes out to be 0.1, okay, so this is 0.1. And what is sine of W? Since W is positive, so this is +1. And suppose this whole comes out to be 0.2. This is minus 0.2. So now, if there was no regularization term, you would have updated this as 0.5 minus 0.2, which is 0.3. Now with regularization, what you are doing, 0.5 minus 0.1 minus 0.2. So eventually you end up with 0.2. So you see, you are ending up with a smaller value when you introduce a regularization term. Many of the students say, what if W is negative, right? So this expression actually works even if W is negative. Suppose W was minus 0.5, okay? And so this would be 0.1, and then sine of W is minus 1, minus 0.2. So you see this minus minus will become plus. So it would be minus 0.5 and plus 0.1 and minus whatever term you have. Okay. So again, when you do this, if you see the number line, so minus 0.5 is here. Okay. And when you add 0.1, you go to 0.4. So you see, in any case, you are going close to zero. Similarly, when 0.5 were here and you are going in this direction, you are actually going close to zero. So irrespective of whether the value of W is positive or negative, this term is pushing you towards zero. Okay. Now, there can be a query that how L1 and L2 regularization are different, right? So I'll come back to that. Let me just give you a recap of these, maybe a clean version in the slides, and then maybe we can discuss further, right? So this is again exactly the same derivation, but you can say a relatively cleaner and typed version. So we said in L2 regularization, you take the square of all the weights, you add them as a regularization term multiplied by a regularization parameter lambda. So since this was our original term from gradient descent, so we have replaced it by J naught, and this is the new term. Okay, so when we take its derivative with respect to W, so again this is the new term that we get. We plug in the equation for weight update, and by some rearrangement we get this expression, right? So as we discussed, this highlighted part is the original term in gradient descent, and this is actually called weight decay, right? Because instead of subtracting from W, now you are subtracting from, say, W and 1 minus 0.2. So actually you are subtracting from 0.8 W, means you are taking 80% of whatever the value of W was, right? And similarly, for L1 regularization, you have a similar expression, but instead of square, you simply add the absolute value. The derivative of absolute value of W is sine of W. So you plug in that in the weight update equation. So eventually you get something like this. So you see this is the new term due to regularization. So rather than subtracting this from W, first you subtract something from W and then you subtract the last term. So as a result, you are actually making an effort to push the weights towards smaller values, right? So both of these are, you can say here. And if we see what is the difference actually between the two, right? So you see in case of L1 regularization, we are always subtracting a constant value from W. Why constant? Because lambda is some parameter, say it has some value, say 0.2. M is number of training example, which is fixed. Eta is learning rate, say 0.001, which is also fixed. So maybe when you multiply them together, you get something, say 0.01. So every time you are subtracting 0.01 from W. If W is a big value, then this 0.01 is nothing. If W is a very small value, then this can be very significant, right? So irrespective of the value of W, you are subtracting a constant value every time whenever you are applying L1 regularization. On the other hand, if you see here, right? So this is actually a fraction of W. So for example, if this is say 0.1 and W is 10, so 0.1 into 10, it will become 1. It means that you will be subtracting 1 from the original value of W. On the other hand, if W is say 100, so 0.1 into 100 will be 10. So it means from 100 you will be subtracting 10, right? So the difference between L1 and L2 regularization is, which is very critical, that L1 regularization shrinks the weights by a constant amount, irrespective of whatever the value of W is. On the other hand, L2 regularization shrinks the weights by an amount which is proportional to the weight themselves. It means if the weight has a high value, whatever you subtract is also a relatively high value. If W is a small value, so what you subtract is also relatively a small value. Okay, so with that, maybe I can take a pause and we can have some discussion. Okay, so now we'll be moving to our, you can say, last topic for this particular discussion, which we'll be revisiting in some of the subsequent discussions as well, but the details we'll see within our current discussion, right? And that is Bash normalization, right? So again, when you see L1, L2 regularization, Bash normalization, right? So there are some derivations involved in this one, right? So what we'll do is that maybe at some point in time, I will give you some numerical to solve so that you develop a good understanding of how they actually work, right? Because just by looking at the expressions, sometimes it is not very trivial to understand what's going on. So maybe at some point in time, I'll give you some numerical examples which you can solve, and that will give you a better understanding of how L1, L2 regularization and this next topic, Bash normalization works, right? So anyways, coming back to our technical aspect. So what actually Bash normalization is, it was introduced in 2014, right? And once in the ImageNet competition, a model was submitted, so it was introduced in this paper, which is titled Bash normalization, right? And accelerating deep network training. So as you can see, the objective is to speed up training. Okay, and actually happened in that particular model was that not only it improved the result, but it improved them with using only 7% of the training steps, right? It means if the model previously was taking 100 epochs, so with Bash normalization you could train it in 7 epochs, right? It means only 7% of the training step gave you a performance which was even better, which you were getting with other models, right? And it's again a very highly cited paper, right? As you can see, yesterday when I checked, so it has like more than 25, near to 26,000 citations, right? Maybe people don't have these many citations in whole life, so this there are some, you can say, highly cited papers in every domain, and it is one of those papers. Okay, now first let's see the motivation behind Bash normalization, that why we do it and what it does. Okay, so before we we can see Bash normalization, we go back to our basic machine learning course, right? And suppose whenever you are doing classification, suppose you have a simple example in which you are in a two-dimensional space, you have two features, x1 and x2, right? So whenever you are using some classifier, so you are normally asked that it's better that you normalize your data. Okay, you normalize the training set. And what actually we do in normalization, you first compute the mean of the data, right? Average, or mean, whatever you want to call it, and then you subtract that mean from every value. Okay, so what actually happens is that when you subtract your mean from every value, so now actually you are translating the mean to the origin, right? So your data is translated like this. Now the mean of this new data is actually 0 0. Okay, so subtracting mean from every value translates your data to your distribution in such a way that the mean of the new distribution is 0, right? So it's a very common step that we do. Okay, the next step that we do is that we compute the variance and we divide by variance, or in some cases we say by taking the square root of variance, which is standard deviation, right? So what it does is that if you divide mean subtracted data or you normalize it by variance, so what happens is that now your data will have zero mean and unit variance in each dimension, right? Now variance, you must know, is the spread. So for example, in this distribution, I have more spread in this dimension and lesser spread in the vertical dimension, right? So it means that the variance is not uniform. I have more variance in one dimension and lesser variance in the other dimension. But when you normalize it, so now you see you have more or less same variance in both horizontal and vertical direction, right? And since at test time we do not have, we can have only one single training example. So it is common that whatever mean and variance you computed at the training from the training data, you can use the same mean and variance for test data, right? Because at test time you may have only one single training example, right? Now, why we do it actually? Again, I hope you know it from machine learning, but I'll just for completeness discuss it again. That you see your features can take on different values, right? For example, suppose you have a feature x1 which is taking values in the range 0 to 1000. On the other hand, the second feature is taking values in the range 0 to 1. So you see the range of values for the two features are very different. It means that x1 can dominate x2 very easily, right? Because when you have values in a very big range, so a value which is changing only by zero point 0.1, zero point 0.2, so that change might not be very significant. And what happens with this change is that since x1 and x2 have a very different range, w1 and w2, which are associated weights with these two inputs, they would also have very diverse ranges. Right? So if you just take some hypothetical error surface, so you see you have more variance in one direction and very less variance in the other direction. On the other hand, if you normalize the input, right? So now it is expected that both both of your, you can say, weight axis, they have more or less similar variance, right? And the impact of this would be that when you apply gradient descent, it will converge quickly, right? So if you have, say, a distribution which is like an ellipse, so you see gradient descent has to arrive here, so it will keep on oscillating, and maybe after a certain number of epochs it is able to find the minimum, right? But if you have the same variance in both the directions, so gradient descent will take a very you can say regular path, and it is likely to converge quickly. This was the main reason that we used to normalize our input, right? But this is not batch normalization. This was whatever I am telling you here. We are talking about normalizing the input, right? That whatever you are feeding to the network. Batch normalization, this was the motivation of batch normalization. And what is that? That we agree that normalizing the input features speed up training because gradient descent can converge more quickly, right? So the idea of batch normalization is that why not repeat the same process for the subsequent layers of the network? That just like we normalize the input, if we have multiple layers in the network, the output of every layer is actually input to the next layer. Okay, and during training, the weights are changing continuously. So just like we normalize the input, why not normalize, or why not do a similar normalization at each of the, you can say, layers? And how can we normalize that? Since normally we use a mini batch for training, so we can compute the average or the mean of that mini batch, and we can also compute the standard deviation of that mini batch, and then we can normalize our activations. Okay, so if I try to explain you with maybe some numbers, so suppose we have maybe a batch size of 3. Okay, so we have 3 examples, 1, 2, and 3 in our mini batch. Okay, so you see, and what is the dimension or of each? Say 1, 2, 3, 4, 5, 6. There are 6 values in each training example. So it's a 6-dimensional feature vector, right? Now, suppose this is not your input, right? Maybe your input was here, and then you have 6 neurons here. Okay, so when you feed your first input, so maybe you get this one, right? For the first training example. When you feed the second training example, you get the second 6 values, and then when you feed the third training example, you get this, right? So these are basically the outputs of some layer, 3 outputs because we have 3 training example. So what we do is that rather than feeding them to the next layer, we can first compute the mean, right? You just add all values together, divide by 3, so you get this mean vector, and you also compute STD. And once you have mean and STD, then from every training example, right? For example, you can do like, if I take the first row, you can do 1 minus 3 divided by 3, right? Similarly, for this one, you will do 3 minus 3 divided by standard deviation, and for the 6, you will do 6 minus mean divided by standard deviation, right? So you keep on doing for, you normalize all the 3 examples, and then you feed them to the training, you can say, to the next layer. Okay, so the key idea of batch normalization is that in a neural network, you have multiple layers. So just like we are normalizing our input data by subtracting the mean and dividing by the standard deviation, we can repeat the same process at the subsequent layers of the network. And since we do not feed the complete training data at once, right? At the input layer, you have complete training data available. So you can compute the average and mean from the complete training data. But during the training, you are feeding data in the form of batches. That's why we call it batch normalization, because you compute mean and standard deviation for every batch, right? That's why this is the term batch normalization, because you cannot do it for the complete training set. Now, another, you can say, important piece of information is that when you are doing this normalization, you are making sure that mean is 0 and variance is 1, right? If you subtract mean and then divide by STD, so you are making sure that you have a distribution with 0 mean and unit variance, right? But in some cases, it can be argued that fixing the distribution to have 0 mean and unit variance can actually limit the expressive power of the network. Means you are imposing a constraint. Okay, so there's a concept that why not let the network choose how to normalize. It means instead of 0 mean and unit variance, let the network decide what is a good mean and variance, which can actually help in learning the optimal weights, right? So what we do is we introduce two additional parameters. They are called gamma and beta, which allow the network to learn any mean and variance. It means you are giving the network full flexibility, that if you want to do normalization in a standard way, you can do it. If you don't want to normalize, that is also possible by some specific values of beta and gamma, and you can choose any other values of these two parameters. Now let's see the details, that what are these beta and gamma and how actually normalization works. So let's see a concrete example. Okay, so we start with the input. Okay, so as we discussed that we agree that normalizing input speeds up training. Okay, so we have all the training data. I can compute mean, I can compute STD, and I can do the normalization, right? Now, when we are talking about match normalization, what is our objective? That suppose this is my layer 2, A2, okay, which is actually input for the next layer, A3. So the question we are trying to address is that if I normalize A2, right, if I normalize the activations of second layer, so will it help in quickly learning or speeding up the learning of the parameters of the next layer, which are W3 and B3, right? Because for A3, A2 is actually input. So just like you were doing normalization here, we are trying to validate the hypothesis that if I normalize activations of layer 2, then it should actually help in learning the weights more quickly for the next layer, right? So let's see into more details. Let's focus on the third hidden layer of this network, where the parameters we are trying to learn are W3 and B3. Okay. Now, if you look at this layer, so you see I'm just hiding the initial part, and this is actually what is happening. This layer is receiving input, which is actually the output of layer 2. But the layer 3 does not know anything. It does not know how many layers are behind. Maybe there are 200 or none. So for this layer, it sees, okay, this is my input. Okay. Now what is happening? Actually, if you uncover this part, so these activations in the second layer, they are actually dependent on the weights W2 and B2, right? And similarly, they are actually also dependent on what values you have in the first layer. So since during learning, all the parameters are continuously changing. So whatever you are getting at the second layer is continuously changing, right? We want to normalize it so that we can benefit from the from the speed, and we can hope to converge the algorithm more quickly, right? So this is basically the objective of Bash normalization, that it makes an attempt to reduce the amount by which hidden units are shifting, because they are continuously shifting due to changes in the weights, right? So if we normalize them, then we expect it to have a positive impact of the learning, right? Okay, so you see in the discussion, we have been using two variables, A and Z. A is actually the output after application of activation function. Z is before the application of activation function. So if you remember, when we draw a neuron, we say, okay, Z is actually simply the sum of you multiply weights with input, you add them together, you get Z. And then you take some activation function, apply activation function on Z, and that is your output, which we call A, right? So there is a divided opinion on whether we should normalize Z or we should normalize A, right? In other words, people have a debate on whether we normalize before applying the activation function, which is Z, or we should apply after. We should normalize after the applying the activation function. So whether we apply A or Z, right? So there's no, you can say, concrete rule of thumb or opinion, but many people actually prefer to apply normalization before the activation function, right? But there are papers in which you will see normalization applied after the activation function as well, right? So it's your choice. You can choose any of these, right? This is not something very critical. Okay, now how do we actually normalize? In a batch, suppose you have 10 examples. Okay, so what we do, we take the mean. This is the formula for the mean. You are adding all the 10 values and you are dividing by m, right? So m in this case is the mini batch size. So this is the mean. And then how do you compute variance? You subtract mean from every value, you take the square, and then you add all the values, okay, and you normalize by the total number of examples. So this is the variance, okay. And now how do you normalize? From each value, you subtract the mean, okay, and you divide by the standard deviation, which is the square root of variance. But you see, this term can be zero. And if you divide by zero, it can lead you to an undefined state. So for numerical stability, we normally in such situation add some epsilon, which is a very small value, say 10 raised to power minus 6 or anything, just to avoid the case that we can have divide by zero. Although it is very rare that you have data which has zero variance, it means everything is actually the same, right? But still, since theoretically it is possible, so just to avoid a situation where we end up dividing by zero, we use this, okay. Now let me just go to the board and explain you a bit more in detail what actually is going on, because let me just try and, sorry, I can't find the board. Yeah, here it is. Okay, so far what we have said, that you have Z I is basically an index for every training example in the mini batch. This we said is that from every example, you subtract the mean of the batch and you divide by the standard deviation, which is square root of variance. And just to make sure that we don't end up dividing by zero, we have this epsilon, which is a very small value, right? Now this step, okay, if you apply this step, what you are doing, you are making sure that you have zero mean and unit variance. Okay, this is the standard way, which you already know, subtracting mean and dividing by the standard deviation, right? But we said we 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 want to do better than that. We want to give the network flexibility to choose any mean and any variance rather than zero mean and unit variance, right? For that, what we do is that we say, okay, let's call it Z tilde. What is this? That you multiply this with gamma, this is gamma, and you add beta. Okay, now what are gamma and beta? These are two additional parameters. I'll explain in more details, right? So these are two additional parameters which are actually learned, right? I'll tell you how they are learned. But before that, let's see what actually is going on here. Now, suppose I somehow gamma and beta, they are learned. So if gamma is 1 and beta is 0, what happens? Actually, you get this. It means Zi tilde is actually same as Zi normalized. So if gamma is 1 and beta is 0, you plug in this expression, you actually get back this thing. It means by choosing a specific set of values for gamma and beta, you can make sure that you can achieve zero mean and unit variance, right? That possibility is not ruled out. It is possible to achieve zero mean and unit variance. If your network wants it, it can adjust gamma close to 1 and it can adjust beta close to 0. Now let's see another scenario, okay? Let me just get rid of this so that we have some space and we discuss another scenario. Okay, let me also plug in the value of Zi normalized in this last expression so that we can discuss better. Say this is, I'm just plugging this value here. Okay, Zi normalized is this, so I'm plugging its value, Ci minus mu under root of variance plus epsilon, right? And here you have gamma plus beta. Now, suppose gamma comes out to be this thing, just a special case, and beta comes out to be close to mu. So what will happen? These will cancel out. This mu and this mu will cancel out, and Zi tilde will be Zi, which means there is no normalization, right? No normalization is applied. So now your network also has the choice that if it thinks that no normalization should be applied, then it can tune the values of gamma and beta in such a way that no normalization is applied, right? So in summary, by using Bash normalization with two additional parameters, beta and gamma, we have given the network flexibility. It can choose to have zero mean and unit variance. It can choose to have any other mean or variance, and it can also choose to have no normalization, right? So maybe we can take a prayer break and then we continue this discussion afterwards. So as we were saying that basically once you normalize the activations of a layer, so rather than having zero mean and unit variance, you let the model decide itself that what are actually the good values of mean and variance. For that, we introduce two additional parameters, which are beta and gamma. So as I told you that now the network has flexibility. If it chooses gamma equals 1 and beta equals 0, so actually you are doing the standard normalization, which is zero mean and unit variance, right? And in a special case, if gamma comes out to be close to this and beta comes out to be close to the mean of the batch, then actually this maps to the identity function, means there is no normalization, right? If the network thinks no normalization is needed, you can actually choose to have no normalization, right? But once you are adding Bash normalization to a layer, so of course it is introducing two additional parameters, beta and gamma, for each layer, where for each unit in your layer where you want to apply Bash normalization. But this number is not very huge, right? If you are talking about a fully connected architecture, then maybe adding one unit causes uh, you can say addition of many parameters, because it is connected to all the neurons in the next layer. But when you are introducing Bash normalization, it is not exploding. The number of parameters would remain manageable because it will introduce only two additional parameters for each unit, right? Just since it's slightly tricky topic, so I'll just explain with one more example, that we see the concrete example of a network, maybe something like this, where we have three inputs, then you have hidden layers, two hidden layers, and then the final output layer. Okay, so what actually goes on? Let's see the first hidden layer. So what actually happens is that you have this x. So this x is actually the vector of these three input values. So using the parameters of the first layer, which we say W1 and B1, W is the weight matrix, 3 cross 2 matrix, and then you have two bias values for the two neurons in the hidden layer. So using these parameters, you multiply weights with input, you add bias, so you get Z1, right? So again, when we see Z1, we are actually talking about this vector Z1 and Z2. Okay, and this superscript 1 here is telling you layer number 1. This 2 here is telling you layer number 2, right? So this superscript is telling you the layer number, right? And when we are writing this Z is a vector. So it means that we are talking about both these values, whatever values you have in the first layer for neurons, which correspond to Z1 and Z2, right? So now you have X, you apply using the weight matrices and the bias, you find Z1, and then you apply Bash normalization to get this Z tilde 1, right? And then you apply the activation function to get A1. So what we are trying to say is that once you have the Z, you apply Bash normalization using beta and gamma, you get Z tilde for this first layer, and then you apply this activation function sigmoid or whatever it is to get this activation, which is actually the output of this first layer. Similarly, for the next layer, what happens? You use the output of the previous layer, which is A1. You use the parameters W2 and B2 of this layer, you compute Z2, right? Again, Z2 is just the dot product and you add bias. Then using beta and gamma for this layer, you will apply Bash normalization to get Z2. And then you will apply activation function on this to get the output of the second layer, which we are calling A2. Right. So in all these examples, as we discussed earlier, we are applying Bash normalization before the activation function, right? Which is common, but you will also find some papers in which Bash normalization is applied after the activation function. Okay. Now, if we see the number of parameters, right? So you see these are the standard parameters that you have. For example, in the first layer, you have 6 connections. So you have a weight matrix of say 3 by 2. And how many bytes you have? You have 2 neurons. So you have 2 bytes values. So bytes is a vector of 2. Similarly, for the next layer, you have a weight matrix of 2 cross 2 because there are 4 connections. And then you have a bias for the top neuron and the bias for the bottom neuron. And similarly, for the last layer, you have 2 connections. So you have a weight matrix of 1 by 2, and then plus you have a single bias because there's a single neuron, right? So this we already know, right, from our basic knowledge of MLP. Now, what are the additional parameters that are included due to Bash normalization? You see, now you will have a beta here and a beta here. Similarly, a gamma here and a gamma here. So for each neuron, you have beta and gamma. So it means that for the first layer, you have a vector of beta and a vector of gamma, and the size of this vector is 2, right? Because you have 2 neurons. Similarly, for the second layer, you have a beta here, gamma here, beta for this neuron, gamma for this neuron. So again, you have vectors of size 2, each for beta and gamma. And finally, there's a single neuron, so you can say beta and gamma for this one neuron at the last layer, right? So when we write these additional parameters where this superscript is telling you the layer number, so please remember, just like W and B, these beta and gamma are actually vectors, right? And the size of this vector depends on how many neurons are there in each layer, right? For example, if in this layer we have 4 neurons, so we will need 4 values of beta and 4 values of gamma, right? Because you have 1 beta and 1 gamma for every neuron in your network. So this is something that you should take care of. Now, if we put all of these pieces together, so you know that when you are doing training, mostly we are working with mini batches, right? So what we do, if suppose this X is your complete training data, so we split our data into mini batches, right? Whatever is your mini batch size, 10, 16, 32, 64, whatever it is. And then to each batch, we separately apply, you can say, batch normalization, right? What we do, we take the first mini batch, X1, right? We pass the training examples in that particular batch using a forward pass. And suppose there are 10 samples in a mini batch, okay? So what then you will do, you will compute the forward pass, and then you will compute the mean and variance. It means you are computing the mean and variance from these 10 samples because the batch size is 10. And then you will subtract mean, divide by variance, and then scale by beta and gamma to get the Z tilde. And eventually you apply activation function to this to compute the activation or the output of this first layer. Then you repeat the same process to the second mini batch, right? You take X2 and you repeat the same process. So you'll keep on doing it on all the mini batches, right? So if we sum up, so whatever is the number of mini batches, you are repeating this process for every mini batch. And what is that process? We carry out a forward pass on the mini batch, right? 1, 2, 3, whatever it is. And then in each of the hidden layer where you want to apply Bash normalization, you apply Bash normalization and replace ZL with Z tilde, right? So this was actually the unnormalized value. This is not normalized, and this is the normalized value, right? And then you use the back propagation to update the parameters just like we have been doing previously, right? So an important or tricky point in this is that you see, when you are performing the forward pass, you need to input the complete batch. Only then you can apply Bash normalization, right? Because if this is my model, okay, so these are my 3 training examples in the mini batch. So you see, I will first feed the first example, then the second example, and then the third example. Only then I will have some values here. Okay, 3 values, and then I can compute the mean. Okay, because I cannot compute the mean with a single value. So when, that's why you see we say compute the forward pass on the complete mini batch, because only once you have passed the complete mini batch, then you can compute the mean. Just by looking at single example, you cannot compute the mean, right? So this is important, and I hope this will become more clear when we actually do a numerical example of this. Okay? Now, if we summarize Bash normalization before going to test time, right? Because this all we are talking about with the perspective of training time, right? So what we have been doing, we calculate mean and variance, right, of the mini batch. Then you normalize by subtracting the mean and dividing by the variance or the standard deviation. And this is just for, you can say, making sure you don't end up dividing by 0. And then whatever you get, you multiply it by gamma and you add beta, right? This is just to give more flexibility to the network, where beta and gamma are learned during training, just like other weights, right? These are two parameters which you update using back propagation, just like you are updating the other weights. Okay? If it all looks very complex, right? But if you want to implement, there's one single line of code that you will add to your model, right? So you have previously been making model where you have convolution and then activation function, right? In between, we just add a layer which is called Bash normalization, and it will automatically do all of these complex tasks. Right? So you see, it looks pretty computationally, and from the viewpoint of understanding, it looks a bit heavy. But from implementation viewpoint, it's very simple, right? Everything is encapsulated in just one, you can say, layer, which is Bash normalization. So after the convolution and before the activation function, you can add this to your network, and you can hope, and you can actually check that your network is likely to converge much quickly as compared to without Bash normalization, right? Okay, so you see, now the last thing which is related to batch normalization is that what we'll be doing at test time, right? Now at training time, you are providing data in the form of mini batches, batch 1, batch 2, batch 3, and so on. So you have maybe say 5 examples or 6 examples in a mini batch, so you are able to compute mean and estimate, right? But at test time, you do not have necessarily always a mini batch. If your model is trained, I can give it only one single training example, and I expect that it will actually give me the label of this example. Okay, so this is my example, and this is my model M. If I feed it, so you see there is no batch at test time. There can be, but it is not necessary that we always have a batch. We can have one single training example. Okay, now there, there's a problem that how do we deal with that? Okay, so for that we'll do something, right? But let me just explain it on the board because it will require some details. So we'll actually use the mean, because you see beta and gamma, they are learned, there is no problem. The problem is, where do we find mean and STD? Because there is no mini batch at test time. At test time, you can have one single example. So what we'll be doing is that we'll actually be using these from the training time, but we'll be using something which is called exponentially weighted average. I will explain in detail what it is, right? Because it is a slightly tricky concept. Now, for some time, now we are trying to understand what is exponentially weighted average, right? So for some time, you can forget about Bash normalization. Just focus on understanding what we mean by exponentially weighted average, right? So you see, I'm sure you must be familiar with every month, maybe different organization release rankings of different teams and players, right? For example, ICC every month releases top 10 batsmen, top 10 bowler, all-rounder, and so on, right? So you see, in all such rankings, the recent performance of a player is given more weight as compared to what they did in the past, right? So for example, if there's a player, maybe he on this axis we have year, say 1990, 1995, and so on, and on this axis we have runs. Okay, so maybe he was performing exceptionally good in the past, right? But maybe recently his performance has dropped, right? So this is maybe 2021. So you see, maybe this was marvelous, but today he is not performing well. So we can't expect him to always remain in the top 10 based on the performance which he did in 1990s or maybe early 2000. Of course, it will have some weight, but this part will have more weight as compared to what he performed in the past, right? So this is basically the general idea of exponentially weighted averages. And how do we assign weights? Suppose a player has played 10 matches. Okay, so score in maybe last match, match 10. This was his scores in match 9, match 8, and so on, right? So this is his most recent match, whatever he scored there. And then as we go down, we are going into the past. Okay, so we want that this performance, whatever his performance was in his last appearance, this should get the maximum weight. And how do we do that? And secondly, this will get a relatively less weight, and as you keep on going in the past, we expect the weights to decrease. Okay, so how do we manage this? We take a variable which is called beta. Please, this remember, this is not the beta that we were talking about in Bash normalization, right? By chance, this is the same notation which we use in the literature, so that's why I'm using it. This is not the beta and gamma that we were talking about a little while back. Okay, so we choose a value of beta between 0 and 1. So the most recent observation will have this weight. The second most recent observation will have weight which is beta raised to power 1. Similarly, the third most recent observation will have this weight. Now, why these weights and how we are writing this, let's discuss in more detail. Okay. Suppose I pick a value of beta, say zero point 0.9. Okay. Now, what would be the weight of the most recent performance? 1 minus zero point 0.9, which is zero point 0.1, into zero point 0.9 raised to power 0. So this is the weight of maybe his runs or performance in the recent match. Okay, then the next one will get this weight, zero point 0.1 into zero point 0.9. Okay, and here you have whatever variable you have. Similarly, the third last performance will have a weight of zero point 0.9 square, and then zero point 0.9 cube, and zero point 0.9 raised to power 4, and so on. If I plot this, so what is happening is this is the last performance or the recent one. Zero point 0.9 raised to power 0 is 1, so its weight is actually zero point 0.1. Okay, so its weight is zero point 0.1. 0.1 into zero point 0.9, right? If you multiply a number with another number which is less than 1, so you are actually shrinking that number. So second last performance will have a weight which is say 0.09. Then you are multiplying 0.1 with 0.9 square. It means it will be reduced like this. So you see your weights are exponentially going down because you had 0.1, then 0.1 into 0.9, and then you keep on multiplying 0.9. You take power 0.9 square, cube, 4, 5, and so on. So this 0.1 is multiplied by exponentially increasing powers of zero point 0.9. So actually the weight that you are giving is going down. And there would be a time when this weight would be close to 0, right? So it means that depending upon what was this value of beta, there is a point after which maybe this performance are not counted today. Okay, it depends on the value of beta that you see 0.9 raised to power say 20, maybe it is like 0. So this, if you go back 20 observation, so these observations will not have any weight. So the idea of exponentially weighted averages is, in simple words, I was just giving you some details of how actually it works. The key idea is recent observations have more weight as compared to previous observations, and weights decrease exponentially as you go back in the past or in the previous observation. And of course, since weights are decreasing, there will be a point where weights would be 0 or very close to 0. So those observations will not have any impact in computing the average or ranking or whatever you are trying to do, right? Okay, now with this preamble, now we can go back to our Bash normalization. Okay, so you see at training time, suppose we are talking about some layer L. Okay, because this will be doing on every layer. So for this layer at the training time, you had maybe batch 1, then you had batch 2, batch 3, and so on, say batch n. Okay, so what we'll do is when we were doing training for this batch, we computed a mean and STD. Okay, similarly for this batch, we computed mean and STD and so on. So for every batch, we had mean and STD, right, at the training time. And during training, your weights are continuously changing. Okay, and once your model stopped, okay, what you did, you actually picked the weights of last iteration and last batch, right? Because your model was continuously training, it had 100 epochs. When the model has stopped, so you pick the weights, they are the weights of the last epoch and more precisely last batch, right? So what you do is you give maximum weight to the batch, and so to the mean and variance of last batch. Then you give a slightly lesser weight to this, then further lesser weight to this, and so on. And maybe it is possible that the initial batches, they don't get any weight in computing the average, right? So in other words, the mean and standard deviation which you computed from many batches at the training time, you will take the exponentially weighted averages of those, and though that final average, you will take exponentially weighted average, let's call it say mu prime, sigma prime, and then you will use these at test time. And why we have to do all this hassle? Because at test time there is no batch, there is a single example on which we have to take a decision. So we use an exponentially weighted average of the mean and STD we computed at training time, and whatever we get, we use it, the computed mean and STD to normalize when we have one single training example. Okay, and how do we do that? Let me also do that before we move back to the slide. So previously you had multiple training example. Now you just have single test example. So I say Z normalize. There is no superscript I, right? Because I we were using for multiple training example. What is this? This is Z minus a mu prime and sigma square prime plus lambda. Now what is this mu prime and sigma square prime? This is the exponentially weighted average and STD that you computed from the mini batches at the training time, right? So let me just write it explicitly. This is exponentially weighted average of mu and sigma of batches or mini batches in training. Okay, now you subtract mean, you divide by this variance, and finally you can compute z tilde as gamma times z norm, which is exactly the same, right? Because gamma and beta you already know, they have been learned. So this is how it is different at test time when you compare it with the training time. So let's just go back and see here, right? So this is basically what we are trying to discuss, that at training time, you have mini batches, so you can compute mean, variance, you can normalize each training example. Here you see I, why? Because you have multiple training example. So you normalize each training example by subtracting mean, dividing by variance, and then you scale by beta and gamma, right? You multiply by gamma and add beta. So this all was possible at training time. When you are at the test time, right, there is no mini batch, right? So that's why we need a different way of finding the mean and variance so that we can normalize the example at the test time as well. So for each layer, since we have multiple mini batches, so the exponentially weighted average of the mean as well as the sigma of these mini batches, it actually becomes an estimate of you can say mu and sigma at the test time, right? And as I told you that the key idea of exponentially weighted averages is that you assign more weight to the recent observation as compared to the past observation, right? And what is the weight factor? That is controlled by a parameter which we are calling beta, right? And this is not the same beta that we were using in the previous expression, right? But since this is a standard notation, so that's why we are keeping it. So the most recent observation has weight 1 minus beta into beta power 0. and then beta power 1, beta power 2. Since beta is a value between 0 and 1, so if say beta is say 0.9 or 0.8, so basically your weights are decreasing, because as you take 0.9 raised to power 2, 0.9 raised to power 3, these numbers get smaller and smaller, right? So this is how you actually compute the mean, estimate of mean and STD for test time. And since at training time you had multiple training example, so I have this I, but at the test time you have one single training example, which is Z. You subtract this mean, you normalize it, you get Z norm, and then you scale it with beta and gamma to get the final, you can say activation or output, which is Z tilde. Later you can apply the activation function and move to the next layer, right? So this actually was related to Bash normalization. I understand it's not very straightforward. It's a bit tricky, right? So I hope that with some practice you will be able to understand it well, right? So now maybe we can take a pause and we can have some discussion if you have any queries.